How's it going, everyone? Welcome. Earlier, again, exploring is this thing called observables, and how do we get here, and why we need to look at this observables. And this is part of the asynchronous nature of JavaScript. In other words, especially when you're writing web application for business, you're not only writing is all of this user interface, which is important, but also is the logic of how you're going to now is exchange data in different computers, in different servers. So that's why it is the next level of competency as JavaScript developers is to be able and capable to know how to handle the concurrency, which is all of these tasks that overlaps at a time, in your asynchronous programs. Now, this actually is a very interesting topic. The reason of, or how do we get here is quite interesting because in JavaScript, at the end of the day, this is run on the browser. So the browser is this application that is running on top of the OS. And most of these OS run several processes, which is our program within this independent resource. And they have something known as threads, which is a small independent unit of works. So how you can do this is like, well, you can think of a process like in your house that each one of those places, the living room, the kitchen, the dining room, and the bath, each one of them allow you to do specific stuff. All right, and they're self isolate, so each one of them has their own resources. On the bath, you have is the paper, toilet paper. You don't have toilet paper in your kitchen. I mean, you can, but the idea here is that put things where they belong to. You don't have the toilet on the kitchen or in the bathroom or in your bedroom. I mean, you can, but again, it's put everything where it's supposed to need, right? So put all of those resources where they belong. And threads are now people that can go through one of these different places. And in this case, people that they can now do is stuff inside of these places. So in the bedroom you sleep, or in the bathroom you go into do the number 2 or 1, and in the kitchen you prepare the meal, and in the dining room you, of course, ate it. Now, these workers, because each one of them, at least from the computer perspective, live in a separate world, they don't change message, and sometimes we need to share message. The way it works on the computer is to say, hey, let's go to now have a particular mechanism or way that allows us to share a message. And that is the IPC, is inter-process communications. So it is safe to assume, let me actually ask Chat Claw here if you know about what it means to. So it is safe to assume that it is safe to assume that process and threads are like a house, and people doing stuff inside of those places, like kitchen, bedroom, toilet, dining, That's an interesting analogy, but let me refine to be more accurate and useful. The process is in this like a house, but more specifically, the process is like an entire house with its own isolated space, resource, and address. Inside of the house, threads are like family members who share the house resource, memory, and files. These family members, threads, can work in different rooms simultaneously, but they are all sharing the same house utility, process resource. However, there are some key differences that make this analogy imperfect, of course. Threads share all memory, they're just not specific rooms. Unlike people who might need to queue to use the bathroom, threads can truly execute in parallel in different CPU cores. And when one thread crashes severely, it usually brings down the entire process. It is like the whole house collapsing if one person makes a serious mistake. Would you like me to expand that? Okay. So, if the process are the space inside of the house and people are threads, okay, think of it this way. The process is the entire house, one complete unit with its own address. Threads are the people living in the house. Each person, the threads, can move work through another example is the hive, the beehive. Each tab might be a thread, and they are all part of the same Chrome house, sharing resources but working in different tasks. If you will also have open world, that's completely different how process, with its own threads doing work there. So another good analogy is the beehive. And the bees. That's really a really good analogy. Exactly. So now the beehive is like the entire process, the entire program, a single containing structure will get its own locations and resources. The bees are like threads, so multiple workers operating with the same hive, and the bees share all of the hive resource, all of the program resource here. So different bees can perform different tasks simultaneously. Some collecting nectar, others building combs, others defending, just like a thread can handle different tasks. However, so the main difference is that real beef has more autonomy than threads. Threads are more like tightly controlled by their process and share absolutely everything, while bees have some individual resource. So would you like to explore that? How would you explain IPC using beehive? So using beehive analogy, IPC will be like different beehive communicating with each other. And here's the main way, whether it's passaging, like bee dance, share memory, like a common flower field, pipe, like a scent trail, socket, like bee scout meeting at a neutral location, and signal, like an alarm pheromonons. The key point is that just like beehive needs secure and efficient way to communicate without compromising their separate colonies, process needs a secure way to exchange data while maintaining their independence. And the reason why we are exploring is this IPC architecture is to understand that despite that all of these applications needs to run in their own process, in this own process here, indeed, this own process, each one of those programs needs to understand and run here. So the idea here is that once we explore this concept of this process and threads, and now with process is this ability to, or is this programs that has its own resource, and then workers are now this individual unit of work that have access and share the process resource. So for example, when you launch Google Chrome and you open several tabs, let's say 10 tabs, so all of these different tabs are being handled by the CPU internal CPU threads, right? Why this is important? Because in the context of JavaScript, this is now a single thread application. It means that it evaluates one line after another, which is a great thing in terms of how do we plan stuff, how do we write code, how do we instruct, how do we communicate, not only to the machines, but also it's to others, developers. So what was the intent to do this? And not only because we're writing is this user interface, and also is to know how can we communicate, how can we defer some computations to run after the next amount of time. So we need to find a way to, so we need a pattern to deal with this. And that pattern is here, callbacks. So callbacks is not a great way, but actually is something that you can do in JavaScript, right? Whether it's on the web platform or the node. We also explore that how can we create our callbacks, and what are the issues with using callbacks, especially when handling is requests in parallels. So we need to wait for those responses to come back, and managing as they came in, coordinated response to show them in the proper order they were called. So this coordination process, which is one of the things that we as a software engineer are getting paid for, is to help the coordination process, and is to find ways to do that. And it can have some true impact on society as a large, because you are not only design is this particular algorithm or this way of coordination, but also you are enforcing that coordination to whoever needs to use that. But in any case, again, all of this design coordinations, imposition is also based on previous work that it comes from the financial sectors and all that kind of stuff. When they figuring out that, hey, if you want to manage your resource, okay, it'll make sense to follow this stuff, this series of steps, this accountability process. In any case, so here, because we need to find a way to deal with this, okay? with this distributed computing, or with this need with this need of sending and receiving message to external system, all right? So whether it is waiting for the user to respond to an event, or from a server, or from some API to, for example, detect change, like Navigator. So when you need to wait for this data, or you want to send data and wait for it to respond, so callbacks here has shown that this is at least one way to do this. It's not great for the developer experience, especially as we now have to handle this more and more complex asynchronous scenarios. Okay, and now we also look at a couple examples of how coordination happens here, and by using data structure to actually define that. To have now some sort of catching that's going to be populated as this data comes in, and then we need to coordinate a response. Again, it requires a lot of work. So not only that, it introduces this problem now as inversion control, because we're passing now is a control to this callback, where we don't have any, so we're delegating control to this. And we hopefully that doesn't trigger too many times, too few times, too early, too late, don't swallow errors, and don't lose data context, you know. And now, even though with callbacks, we have an additional problem that they not only are hard to reasoning about, but also is that this time coordination is something that we need to do, and that is not a pretty easy stuff. So thunks say, all right, you know what, this is a problem that other JavaScript developers, so this is something that way predate JavaScript, because previous computer science say, hey, you know what, we need to handle this problem, all right? And they come up with this thing called thunk. I don't know where the name come from. I don't know what they're smoking. I would like to have some of it to actually absorb all of the things quickly. But thunks is based on the premise that we don't carry, or we want is to eliminate time as a complexing factor. So in other words, that when we are firing up several AJAX requests or communicating to external systems, I don't know when that happened. I just only care that when that happened, I get the value there. So we look from the synchronous perspective and for the asynchronous perspective. So for the synchronous perspective, thunks allow you to now have a token, which is thunks at the end of the day is just a function that wrap another function with everything that it needs, and when you call that thunk, you will get always the same value. You will get the same data. You can get the value out of this. Whereas with asynchronous perspective, it's pretty much the same, but in this time we're going to pass a callback, and by the time that that is done, we can now get the data by passing the callback, right? So even though the thunks eliminate time as a concerning factor, which is a huge thing, all right, still we have now the problem of inversion control, and they are hard to reason about it. So that's, we look here at promise, where now promise is coming from the programming language called E, which was developed by Mark Miller, which one of the contributors to create this language called E, where the idea is to actually know how can we deal with this asynchronous nature, and that's one. So they have something called features, and here in JavaScript we have something like promise, right? So where the idea of promise is that, hey, we need some sort of placeholder, okay, uh, that allows to eliminate time as a complexing factor wrapping around a value. So in other words, this is pretty much like if I walk by to my favorite restaurant, my favorite pizza restaurant. So I walk by to the counter. I ask the lady, "Hey, I'd like to have a chili pizza," right? So the lady say, "Well, that'll be $1.1049." So I hand over the money, and what I'm expected to get, well, it's not the pizza. What usually happens, I get is a receipt with an order print on it, and that will represent now an IOU from there to myself. So this doesn't stop me from thinking about how wonderful my pizza will be and all of these dancing pizza slides and all over the place. So I'm famished. I can't wait to eat. So suddenly, magically, all of this. So the order is the order number is announced. So I walk back to the counter, receive at hands, I hang over it, and what I'm getting instead is now the chili pizza. So promise is these abstractions, and now promise, you can think of this as a callback manager or an event listener. And I think this is very important concept, because this is now give us the idea of what's truly going on. And that is that at the end of the day, the problem here is coordination. And now how promise actually give us this trust that we don't have with callbacks, all right? And that is, hey, promise around only once, and they're not gonna fire too often, fire too many times, fire too late, or too early, too late, too many times, too few times. Don't lose data context. Don't swallow up errors, right? So this is not the guarantee that we have with promise. So we now have is control. So the inversion control problem. Now promises solve that. So that's great, because we went over to not only describe that promises at the end of the day, right? Let me see if I put it here. Exactly. Promises are the codification of an idea that we need a placeholder to eliminate time as a concern wrap around a value. Wrap around a value. So let me see if I put it here. Synchronous promise. I think I made it here. No, it's a little bit later here. All right. So if promise solve the inversion control issue, okay, something that we're gonna talk about later about generators, but promise solve this issue, right? And now provide us is a control flow and a data flow by subscribing to those promises. And when you subscribe to that then and then return a new promise, you actually describing is a change of data flow and control flow, which is a great thing, right? So now we have all of these abstractions like all settles, all, and all says that, hey, I'm going to fulfill if all promises are fulfilled, and reject if any is rejected. And in contrast with promise that all settle is that, hey, I'm going to fulfill all promise settle, whether it's fulfilled or rejected. And then you have now promise.raise, which say, hey, I'm going to fulfill is the first promise to be resolved or rejected. right? Okay. Exactly. Let me actually put at this. So if you don't, so just to not lose my mind, I can say is this. So here we have now a particular example. We say we're creating is this promise, right? And here we're saying, hey, you know what? After next amount of time, I want you to now resolve this with 500 seconds, then 100 seconds, and then 200, right? So what will happen here is that it's going to now trigger this, all right? And then you're gonna catch this particular error. But as you can see, is the first promise that was resolved, you know, promise.raise. However, if we say now this, and that'll be quite interesting, if both promises are resolved fairly the same time, so let me actually now do this. So if the second promise is resolved is after 1 millisecond, all right? So now error is emitted here. You know, whoever was resolved whether it is rejected or resolved is going to get that, which is great. And then you have now promise.any. Okay, so promise.any we're gonna get okay. So we'll resolve the first fulfill promise or reject all of the promises. So the subtle difference between the raise and any is that raise will say, hey, I will give you is whatever promise was resolved or rejected first, whereas any say, I'm going to give you is the first promise that was resolved. The first promise that was fulfilled, okay, or reject all of the promises if all of them are rejected. So again, all of this abstraction, which is very, very needed as you're going to now handle this asynchronicity in your applications, right? It also now still has this thing or this issue that we need, even though now it's much better than callbacks, we still have the problem of that is non-sequential and non-reasoning about it. So what happened is with promise, and as a way to move on to the observable at once, which is what we really care in today's video, we looked at now because promise is now a concept from the functional programming, which is a monad. And I can describe this in terms of its functionality, at least one use case, which will allow us to describe is the state the state change. Okay, so much like promise, but in this case is for one. It only fires once. Okay, hey, if this data is resolved or rejected, this is it. This is how you can subscribe to this. And then we enter into the concept of functional programming and all that kind of stuff. Again, this goes beyond the scope of this. And I think this is quite important, quite interesting to dive deep, because what functional programming gives you is now the ability or the guarantee to have predictability in your code. And of course, to have a well-maintainable and easy to test code. Now, but because this is go beyond to the scope, and I think this is something quite interesting to explore later on, we went through to look at the this problem, which is what promise has of describing is this different .then or the chainable .then, where inside of this we can pass some functions that return some promise. Okay, but these functions might live in different models and different files. So what promise says, if you're the ones to write this in a more modular way, you say, hey, once I get this, then I need to handle this scenario. Once I get this, I need to handle these two things. So these things I want you to send over to somebody else, and this I want you to now split that to make some transformation, that kind of stuff. So as you can see that if you have now this split in different files, it becomes quickly a nightmare. And it's harder to follow the path. Now, because these problems of non-local, non-sequential reasonability or reasonability issue that now give us here is the promise, okay, where now with generators and this concept that it was introduced in EX6 to actually now make it easy to describe is a recurring pattern that we need in the language. So generators is the ability to pause and resume functions, right? So the idea here is that because our functions run to completion, which is a great thing, so we make sure that all of these statements are wrong, and when you have a function inside of another function, well, you just call that, you create now a new function execution context with its variables and its memory reserves, all right? And then you now add that to the call stack to understand, hey, in which part I am currently in the code, all right? Get into the function, continues to evaluate in that. And if that has another function, let me add that now to the call stack so I can keep track of where I am in the code. Go and open now a new function execution context, or create a new function execution context. It continues to evaluate if it is a statement, right? until there is no more functions to be called. So once you run to completion, you remove that from the call stack, you go back to where you were evaluating in the previous functions, continue to evaluating until completion, right? And then you go remove that from the call stack, and then you go back to the evaluation of the previous first function, and you continue to evaluate your code. So this is something that is quite interesting in terms of how do we now plan stuff and things, okay? And this machine is something quite interesting. However, sometimes we need to have the ability to not run to completion. And this is not necessary to bring chaos to the language, but this is to describe is now this behavior that we need. So generators, after all, is the need to have a way to describe syntactically a state machine. So in a state machine is just a way to describe a pattern of series of flows from one state to another, to another, to another, to another, and descriptively lays out the transactions. So why this is important, you may wonder. Well, because now with generators that give us the ability to pause and resume, we can do that without using that. And we need to use these callbacks and iterators. And for those who are not familiar with iterators, well, iterators is just a design pattern for typically stepping through data. So for example, when you're querying database, for example, you're using on the select, because I am not quite familiar with databases. That's what happened. How can you describe how you can describe the SQL or fetching data pagination in SQL as a way as a software engineering, I want to understand is the iterator pattern, which is a behavioral pattern. For handling large data sets efficiently. Exactly by the offsets. So you have the limits and the offsets. So here you're telling now to the database, hey, select all of this columns from this table and order them by its ID. And then because you might have huge amounts of records, and if you can think, I will invite you to go to some of these lawyer firms so you can see the huge amount of paperwork they have to deal with. It's like it's insane, man. Yeah, it's insane. So instead of having all of this physically, right, we have all of that now digitally. And because we don't have this sense, we have the false sense that we don't touch that, you know. But this is a huge a pile of paper or documents or the records that we have in our tables here, okay? We need to actually fetch that in chunks. All right. This is now iterator is a great way to describe now describe a behavior needed to fetch data in an efficient way, chunks of data for handling large data sets. I think that's very interesting here for that. Let me see, is there any website to test SQLite queries against a demo table? That'll be interesting, by the way. DB Fiddle, SQLite Online, SQLite Interactive Tutorial with Building Exercise, Lead Code, Problem Set, Database, Practice with Real Interview Questions, SQLite Zoo. Okay. Combining two tables. Okay. Yeah, why not surprise? Interesting. DB Fiddle here. Oh, interesting. SQL Server. Distinct IP address. Darling data. SQL servers performing tuning. Down right. Okay, Postgres. Select version. Interesting. Interesting. I am at DB Fiddle here. I am a DB Fiddle and I want to do a test query like so. Yeah, you get it. Okay, this is to create a table. Okay, this is to create a table, right? And then select that from this. it run. Holy moly, look at this. And it works. Okay. So this is a good example of now this particular pattern here. Right? This particular pattern here. And because I already made that, what I can say now is updating the limit here. 10, and now give me the 10 next one. Right? And it's quite slow, as you can see. Oh, interesting. Interesting. Oh, it's because it's from the scratch here. Okay, it's because it's from the scratch here. Okay, that's quite interesting. Very, very interesting, by the way. Exactly. But as you can see here, with this particular pattern of stepping through data through iterators, which is now is a concept from Python, now this is something that we can actually simulate or recreate in JavaScript, but with generators we don't actually need that, and also it's because it requires careful programming to actually do that. So now generators here, as the name suggests, is not only is for generating values. So anytime you define a generator, you get in here and when it finds the GL keyword, it will now freeze, stop everything there, block that function, not the entire UI or the main thread, and then when you call that, when you resume, it continues to evaluate until the next GL or until the return. If the return is not there, functions always return something, even though if you don't tell them explicitly to do so. So it will return undefined. So this ability to pause and resume, pause and resume, pause and resume, which is a great thing because also you can now pass some data to that, and from the perspective or from the internal perspective of the generator, because anytime you create now a generator, when you run that, you get is an iterator, which what allows you to control is the execution of these functions by using is the iterator protocol, which is you have now the next methods that actually is the way of how you can pass data in, and if you want to get some data, you access to the .value method from that. So this messaging passing, which is great, and is more interesting using generators as now handling is this asynchronicity, okay, which I really think this is very, very interesting. And in fact, I also made a couple examples of how you can use generators for that to actually create that. Okay, so this is pretty much when our logic is going to be created, and because whoever controls the iterator now can have access to that generator, you have to be careful about who controls it. So you don't want to pass this control to multiple places, okay? Because you might have in a wonky state. So in this case, we have now this iterator that is generated here, and by evaluating this iteration and return now a promise from this, which is here, and then we subscribe behind the scenes to that promise, and by the time we get that data, we now is trigger or we resume the function execution like this. All right, so you can get now this data as data. All right, and here's where actually is now handling is this promise like, So we are using is this flow control here, and saying, hey, you know what? By the time that we get this data, listen, the streams of that, because that's what happens. So the server is now sending all of these chunks of data, and now the client here is actually putting that on the buffer, so it can now have in the store all of his data here in this response, because all of this data comes in so the response object here, response object, no, the response, because the response object now is this, an object defining a body of the response. This can be null, okay, and this is quite optional, right? So in our fetch response example, fetch response live, we create a new response object using the constructor, passing it a new blob, right? So you might wonder, well, what is the shape of this? Well, is this, right? So the shape of this, so it creates a new response object, okay? And this new response object contains this. It contains the body, which is a readable stream, the body used, the header, which is something that we receive first, and the status. Because on the body, which is the payload, we receive that as a readable stream, streams of data, and these readable streams represents readable stream of byte data. The Fetch API offers a concrete instance of the readable stream through the body, property of the response object. So because we are receiving is these streams of data as byte, okay, we need to find a way to actually read that data, to make it in a usable format for the application level. And that's what we use, for example, getReader. Like, so create a reader and lock the stream to it. While the stream is locked, no other can be acquired until this is one release. So because we receive these chunks of data, okay, and I think this is a good example of this, right? Because we receive this as chunks of data. In fact, let me actually put this at test, so you can see that I didn't lose my mind. You know, let's go for here, right? This is the JSON in a usable format way. Let's go to now the console, or in this case here. All right, let's go here and fetch this data, attach it to now, wait, what? Fetch this data here. In fact, this will be now the response, okay? So if I want to now read the response, which is of course a promise, now I have to subscribe to that. So it means that, hey, by the time you have now this data, okay, I want to now have access to that data. So this is the response, right? So I'm passing this callback to get the value out of this, to get the response, right? So it's okay, cool, this is the response, but the body is in a readable stream. So if you say, hey, yeah, but I want to get access to the body, right? It's this is now this state, right? I lock this. So this body, which now represents a readable stream, a streams of byte of data, okay? You might wonder, is like, how can I then read the data from this? You know, how can we read the data through this? And that's a very good question. how can we read the data from this? So you can say, hey, all right, so the return value is a readable stream default reader or a readable stream by a reader. So because we now get the reader, so it logs that, so nobody can actually read that for that, which means is that, hey, I log this, so I log this, and good luck trying to do something else. Right? So the reader here, get reader, as it is, which return is a readable stream default reader. So because the body here is now in a readable stream. So you say, hey, this is the readable stream, okay, which is the body. Because the body is a readable string, which represents now this strings of bytes, okay? We want to find a way to actually get into that. And that is, hey, I want to now have access to the reader. So when you summon, when you call this get reader methods, okay, you are behind the scenes say, hey, I want to lock the stream to it. So while the streaming is locked, no other can read, so no other reader can acquire until this is one release. So hey, block this reader or block these streams until I finish that, and then it's going to expose now certain methods here. The readable stream default like this. So this readable stream default reader, which is now the readable default reader, okay, now it's an interface of a string API representing as default reader that can be used to read a string of data supply from a network. So the get reader, what it does, so this readable stream say, hey, this is how can we represent a readable streams of byte data. Okay, this is the class that represents this readable string of byte data, and they have some methods from that. And get reader actually is now say, hey, I'm gonna lock this, and I'm gonna expose some methods until I finish read that. So this expose some method of the readable stream default reader that now represent the default reader that can be used to read streams of data supplied from a network, such as fetch requests. So now with this interface, all right, we can actually read to that. That's very interesting. So this reader that now give us is so that now this method get reader say, hey, I'm gonna lock this streams of bytes or streams of bytes, and then until it's released, and then gonna expose you some method in class so you can actually read that streams of chunks. So that's great. So for example, is this one. You can say, hey, I want to actually now read that data. So the reader dot read. So now the reader dot read return is a promise, okay, which is a great thing. So the read returns now is a promise, that we can safely return here. Okay. And look at what's going on here. We are now changing all of these instructions here, where there is nothing wrong with that. But again, we need to look at this code, and if you want to make this code reusable, you might have to throw that into a particular model or a particular module. Exactly. Now, because I'm gonna get these values here as a promise, okay, by the time you get that value, all right, the different possibility is this: if a chunk is available, the promise will be fulfilled with an object of the form value the chunk and done. And here is using now the iterator, as you can see. So we can read them, all right. So if this is done, string complete, para.text content result, and return nothing. Value of fetch streams in an UTI string. Exactly, this is what I want to, okay, this is now the object that we receive here. The shape of the data that we receive here. We receive now here an object that contains done and value, and all I want to do is console.log the value, right? And as you can see, this is how do we receive this kind of data. You know, this is how do we receive this kind of data. We receive these streams of data as it is, you know, and then we need to transform these streams of data into a readable chunk, bro. Into a readable chunk, bro. So we receive these chunks of data as it is, char receive plus equal value.length, const chunks equal to the value, let list items document create elements, and then you're gonna append all of this. I think this piece of code is actually quite illustrative in terms of look at what's going on when you are now fetching data in a simple, silly way, right? That's gonna use this. No, in fact, it's this one. All right, and on the response here, okay. Look at this. So I now call the response here, and then you get it, all right? And here is actually now reading all of these chunks of data. The question is that, okay, so now that we get all of these chunks of data as a string, as a byte, good, that doesn't make sense as human. So how can we actually now transform those chunks into something that I can understand? You know, UTF decoder here. Ah, there you got it. This example shows that how you might fetch a text file and handling is a string of text line. It deals with strings chunks not ending on line boundaries, and with converting from uint 8 array to string. All right. So because we know that this is how we fetch this data, or how we read this data, which is a great thing, okay? And I just want to illustrate all of that chunks of data, okay, as it is. And in this case, you can say, hey, I want to define is now this h1 here, h1 here, followed by this h1 here, okay. This is example. You can say fetching data. Exactly, to illustrate stream bytes of data, right? And here we're gonna now show is this list, right? In an organized list where you say, hey, this is now an order list. With this, right? And here I just want us to now say, well, do this. This will be is now stream all right. And here after that we say, hey, I want you to now get that element, document get element by ID, all right, called stream. Get now the element, all right, and then let's go to now append that element dot append child of this new element that I'm going to create right before this, which is the this is the unordered list. The unordered list. And here I'm going to create list element here, list item. Hey, I want you to create now document dot create element list, and then append that, and then you say, hey, the text content will be now the value, and then I want to now append that element right below this. You can see you have all of these chunks of data here. Massive, bro. Massive, bro. Exactly. We can wrap this like this to say, hey, I want to show now in this particular way. Like this. Poof. You know, you have all of this data here. But again, this is what represents this data, right? So this value that represents is the chunk, no, right? So this value that represents is chunks of data. But this is important to at least to understand this, right? So fetching data as streams of bytes, stream bytes. Exactly. So illustrate data fetching stream bytes, because that's what I want to do at the end of the day, you know, with this particular thing. So all right, so again, this is most likely to understand how do we fetch this particular data, all right, and how we need to actually is transform these collections of bytes in the streams into something that is usable for us, into a JSON. And to do that, to avoid block the main thread, we're going to use a promise for that. We're going to pass that to the callback queue, to the microtask queue, to say, okay, good, now after you're done, all right, give me the data that I want to, and pass that. And as you can see, this is how we're actually showing our data. This is quite interesting and powerful because this is now, for example, some applications like Redux Saga. So Redux Saga, for example, is trying to do, okay, by saying is that, hey, because the entire, because state management and running side effects are quite different animals, Pokemons. We need to find a way to effectively solve those problems. So yeah, this is quite interesting, and perhaps now companies like Next.js actually are pushing forward more of their frameworks to actually build these kind of applications, and I think this is merges of complexity. This is just my opinion, but in any case, yes. So after we look at that, which is quite interesting, and understand that this is good for handling data in a blocking sequential way. So that's the value proposition of generator at the end of the day. And you can simulate now is what async and await behavior is doing behind the scenes, which is now using these concepts. When it comes to handle this now streams of data from a source, which is something that happens a lot in our code base, whether it is stream of data from the users or from the server or from any other external systems. Can promise help us here? We look at example that by wrapping a promise and then now by wrapping a promise around the source of this event and then now calls that, it only works once. So promise fires once. So what we can do is to say, hey, you know what? Let's go to now is encapsulate this promise inside of the event source. So we define the setup logic and the emitter there, or the subscriptions there. But the problem is that why we need to do this, and not only that, because if you want to then expose this promise to the outside world, then you need to have some sort of state to actually keep track of that, of those, trying to expose that, and all of a sudden we are where we are. We are at the beginning here in our coordination problem. Okay. So what happens if we use, for example, some lists? So lists, despite that this is being good to do that, because that's what we can do, is to process now how all of this different stuff, all of this different data comes in. We want to now perform some computations or data transformation. Here, if we want to use that at some another location in our code base, we are now tied to this. So now, how can we actually have the ability to now set up our event source and the consumer in different places, so we can now work with them. So here enter observables, and now observables is now in a current state of this proposal. Okay, they're not right now something that are widely available or spread, all that kind of stuff. However, there's some works that needs to be done. There's some works that needs to be done. Okay. So there's some work that needs to be done, especially this is in a proposal stage, in a draft state. So the API that we're going to see about this is not currently natively supported, but it's one of the libraries that the new specification, the new spec are going to be used to implement that. Okay. So because this thing is going to continuously evolve, right? But the great thing of this library is that you learn once and run everywhere. So some smart folks and Microsoft actually wrote this, and now initially we were working with that in Java, and then you have now on C# and then Python in Python and JavaScript, which is a great thing. So we're going to see of the conceptual description of observables, what an observable is, all right, and how now observables is pretty much like the spreadsheet. Who doesn't love spreadsheet? I do, man. I really do. I completely really do. So here there's some random spreadsheet here, where the idea is that on a spreadsheet you can have now fields with values, and fields with calculated fields. Okay, so now these calculated fields can be based upon on another field. So let's say now C1 has a value, and then on C2 you add, so C1 has a value of 10 on it, and then C2 has a value of C1 plus 10. I'm going to make C1 plus 2, and when we hit enter, as soon as we hit that, we get immediately the calculated value of C2, which is 12. So, and then you have suddenly another field, C3, that says, hey, this is the calculations of whatever is on C2 times 3. So C1 is 10, C2 is 12, and when we hit now enter on C3, well, it is 36. So you see these calculation steps in a flow of data. And that's quite interesting here, this flow of data that you're putting in this calculation. So we're doing a flow of calculation data from the source and doing a series of calculations to response of that data. And this is the genesis of reactive programming, which is huge, especially if you want to now handle this thing called race conditions. Or how do you handle now is streams of or series of events from the user or from the server, from any external services or systems. Okay, so the source of my data is this event source, but the data, once I get through a series of steps, and some might be immediate response, and some of them might be a synchronous step. So this particular step that my data is going to pass through, that some of them can be immediately response on the spreadsheet example, or asynchronous. So as a UI specialist, we need to deal with events from the user and the server. So an observable is a way to model the need to, similar with promise and generators, okay, where an observable is a way to model the need to hook up to okay, it is the need to receive a single unit of data from an event source, and all the step and pass it to all the step and pass it through all the step to propagate its way to the systems. So it is a data flow mechanism. But that's the need here. How can we now get a single unit of data from an event source and pass through all of these steps and propagate through the system and propagate its way to the system? So if we have an event-oriented system, this might be a good abstraction to go with. So let me boil down for you. So an observable is an adapter hooked into an event source that produces a promise every single time a new events come through. And I think this is quite interesting to think about it. This is technically speaking, right? Technically speaking, an observable is this. So an observable is an adapter hooked onto an event source. Technically speaking, we're describing is what it is, not why we need this. So why we need this is because we need to find a way to process this data, this single unit of data from an event source, and pass through all of these steps, and to propagate its way to the systems. This data flow mechanism. So an observable, okay. So let me boil down for you. So an observable is an adapter hooked to an event source that produces promise every time the new value comes through. That's quite interesting. That's a very, very, very interesting thing as it is. So that'll be all for this video. Take care. Bye-bye.